bonus content. I don't know what we want to call this. So this is stuff not going to put on the final, okay? But it is kind of, machine learning, still relevant, still useful stuff. I will be teaching 101C in the maybe I 101C in the summer, I think, or am I not? Now I just got scared that as I started saying this that I don't know what my summer schedule is. Let me just check. I just got scared. Uh-oh. So it's funny. Okay, yes, I am teaching 101C and 102A. Yeah. Okay. Session A and session A. Okay. Yes. All right. Just slight moment of panic that I forgot what I was doing. It happens. Okay. So if you take 101C with me, I will cover kind of different machine learning topics but definitely from a practical standpoint, and get less into the algorithms that like we did in this class. And so we'll take a look at modeling our data with, say, like R and tidy models and things like that. Okay, so a decision tree basically takes your data and then and it asks these questions, and using those questions, it splits the data into smaller subsets, smaller chunks, and so basically at each question, you can either answer yes or no, and and it will partition the data based on that. And then, so it says at each split, the tree uses one explanatory variable and forms a binary split using a simple rule, and that we create branches. And your binary splits could be something like, if you have a numeric variable, it will be, is x greater than k or x less than k or something. So it could be like age, is the person over 30 or under 30? And that will form kind of two groups there, right? And if you want more than two groups, then you'll have to do further splits. You'll have to do, is the person over 30 or under 30? And then you'll ask for the people who are over 30, then you ask another question, is the person over 50 or under 50? And then you'll get, then you'll end up having kind of three segments: under 30, between 30 and 50, and then over 50, type of that, okay? And then if you have a categorical variable, you would split, you'd basically say, is it in this category or not, right? So you'd say, is the person from US, Mexico, or Canada versus everywhere else in the world, okay? Or something like that, right? So is the person from, California, yes or no? Is the person from a West Coast state, yes or no? And then you just kind of keep splitting the thing with these yes or no questions. And then after you feel like you have enough splits, then everybody who is in that final bucket will share a predicted value, okay? So it'll be kind of like, and so this kind of stuff happens frequently, I guess, in like politics and demographic studies and stuff. So you'll say so it kind of treats, for better or worse, it'll say they'll talk about different segments of the population. And so it'll be like, suburban, college-educated white women vote this way, okay? And it will be kind of like, is the person live in a suburb, yes or no? Is the person college-educated, yes or no? The person white, yes or no? Is the person a woman, yes or no? And then, that forms a kind of a bucket. And then they'll say that segment of the population, 70% of them voted this way, 30% of them voted a different way. And so if you hear somebody fits within this certain bucket, then you will predict they're going to vote this particular way. Obviously, not every single person in that bucket votes that way, but you might have kind of these things, and they'll say other things like, whatever other kind of segment or demographic bucket somebody wants to create or something. Okay, and that's basically decision trees. Is like creating these different buckets and things like that. If it's a regression tree, you would put in, you predict a numeric response. So regression trees are not particularly good at predicting things, because let's say you get 8 separate buckets at the end. You have like 3 variables, and each variable has a yes or no. Basically, you're going to get eight different buckets at the end, kind of. And you can only predict 8 unique values. Okay, everybody in this bucket we predict gets the value 1.7, and everybody in this bucket we predict the value 2.3 or whatever. Okay, you only get 8 unique values there. And then but classification trees can be useful, especially if you only have like maybe 2 or 3 categories in the response variable. You might have enough kind of buckets to do this. But let's talk about how decision trees are even, like, how do you choose the criteria with which you use to kind of split your decision tree and things like that. Okay, so we'll take a look at a numeric response, and we'll look at splitting a regression tree based on a numeric variable. And the way the decision tree algorithms are generally written is that they are written to be greedy. Okay, and that is, you calculate your residual sum of squares in the beginning, okay, and then you consider all of the different possible splits you could make, and then you calculate your residual sum of squares after making the split. Okay, and whichever split minimizes your RSS, that's where the decision tree is going to make the split. Okay, so here's an example of a decision tree that was run all the way back in 2008. So I don't know how old you guys would have been in 2008, but that was when Obama was first elected, and during that time there was before the presidential election, there was a primary, a Democratic primary, and it was Hillary Clinton versus Obama during the Democratic primary, and Obama eventually won that and eventually won the presidency. But it's kind of fascinating, because if you didn't know that who the candidates were between, and you looked at these questions, it reflects a very different kind of like picture of America back in 2008. So some of the questions it asked was, is the county. So this was a decision tree that was published in the New York Times back in 2008, and what they were trying to do is they were trying to figure out who might win the Democratic primary, and it was kind of like halfway through the primary season. So before clear winner was decided. So like this year, we already know who's going to be the candidates for the Republican Democratic parties, and it's just the convention is coming up. I guess national conventions are coming up when they finally make their things, but kind of earlier on in the process, like a few states vote, and then more and more states vote, and as that goes on, you get a clearer picture of who might win. And so this was kind of done, in the middle of the Democratic primary, where some of the states had already voted, and Obama had won some of the states, Clinton had won some of the other states, and things like that. And they were trying to figure out, like, okay, with the remaining states that will vote, who might end up winning the primary? And so, questions like, is the county more than 20% black? Yes or no? Yes. Obama won those counties, 383 to 70. Is the high school graduation rate higher than 78%? And if the answer was no, okay, then Clinton won those. Hillary Clinton won those counties. Is the high school graduation rate higher than 87%? So it's kind of interesting. They used the same variable of high school graduation and kind of segmented it at 78% and 87%. And if it was higher than 87%, they said this is a highly educated county. Obama was more likely to win those. Versus high school graduation rate of lower than 78%, Clinton was more likely to win those. Where's the county in the Northeast or in the South? Clinton was more likely to win versus in the Midwest or West. And then they asked questions like, in the year 2000, were many households poor, being earning greater than or less than $30,000 in the year 2000? And then yes or no and things like that. And if it was kind of what's the population density, if it was a higher density county, Obama was more likely to win. And then who won those counties back in 2004 for the Bush versus Kerry election, and things like that. So kind of, I think looking at this, if you didn't know who was on this side, who the faces were, I think you might predict somebody else. Okay, but how did it come to determine like it should draw a split at say 78% or 87% and decide which of these variables to use? So I wanted to kind of dig into that a little bit, and so to kind of illustrate what's happening, I have this toy example for a regression tree. Okay. And so here we have x values. X is 1, 2, 3, 4, 5. And the response values, y, are 1, 1, 3, 7, 8. And what we want to do is we want to figure out, like, where should I split the data to kind of maximize the I guess my gain, or minimize my RSS after the split. So we start with kind of this baseline value. Okay, the baseline is before a split's even made, all of the data will belong to like one bucket, one partition, and you would just make the same one predicted value for all of your observations here. And so in this case, we would take the y's, we would average all the y's out, okay? And this averages all the y's add up to 20, and so our mean for y is going to be 4. Okay, so we would predict 4, our y hat for everybody would be 4, and then I would calculate our residuals, okay? And then I would square my residuals. So with no splits, I got a residual of 3, 3, 1, 3, and 4, and I square those, I get 9, 9, 1. 9 and 16, and when you sum those up, your total RSS with no partitions is 44. Okay, and then what we have to do is we have to consider every possible split that we could make. Okay, so we sort all of our x values in order from least to greatest. Oh, here's a picture of the values. 1, 1, 3, 7, and 8 for y, where our x's are 1, 2, 3, 4, 5. And then right now our mean is 4, okay, and so our residuals balance out, and then we squared our residuals, we get a squared residual of 44. Okay, we're going to consider all possible partitions, so we put our x variable in order from least to greatest, and then we'll consider a split between x is 1 and x is 2. So I consider a split between x1 and x2. And then the next one I would split between 2 and 3. I would try a split between 3 and 4, and a split between 4 and 5. So I have 4 kind of partitions to consider. So here we're going to make a partition at 1.5, x equal to 1.5. And so that's going to form kind of 2 buckets. Okay, I've got bucket A, where I have one value in there. It's just y equals 1. And therefore, my predicted value for bucket A is going to be 1. And if I do that, I have a residual of 0, a squared residual of 0. If I split at x equals 1.5, then these four observations, 2, 3, 4, 5, are in bucket B. Those y values are 1, 3, 7, and 8, which gives a mean of 4.75. I calculate the residuals there and square them, and I add them up. And the total squares of these residuals is going to be 32.75. Okay, so again, we predict the same value for everybody in this bucket in these four observations, and this is what we get. Okay, does that kind of make sense? All right, and so this is kind of the picture there. These four are together. Here we got no residual here. Okay, I can try a split between 2 and 3. Okay, and between 2 and 3. In partition A, we have these two observations, and so y is 1, y is 1, so I'm going to predict 1, and I get 0 squared residual there. And in partition B, I have the observations 3, 7, and 8. The mean of 3, 7, and 8 is 6. 18 divided by 3 is 6, and so my residuals are -3, 1, and 2, and then I square those, I get 9, 1, and 4. And so the total squared residuals here is going to be 14. Okay, and this is kind of the diagram there. If I split between x is 3 and 4, then in partition A, my three observations are 1, 1, and 3. And in partition B, my observations are 7 and 8. So the mean of 1, 1, and 3 is 1, 1 and 2/3. And these are my squared residuals, 0.44, 0.44, and 1.778. And then over here, my y hat between 7 and 8, the mean is 7.5. And so my squared residuals are going to be 0.25 and 0.25. And when you add everything up, the total RSS there is going to be 3.1667. Okay? So these are your residuals, your squared residuals ends up being 3.1667. Okay, and then lastly, we would consider split between x is 4 and x is 5, and our y hats here are 3, and you square your residuals, you get 4, 4, 0, and 16. Over here, we predict 8. Squared residual 0, squared residual 0, and then you add that up and you get 24. Okay, for your squared residuals. All right, so looking at all of the different splits, the best split happened between x is 3 and x is 4. Okay, and our RSS after the split there was 3.1667. So that was the best kind of split, and that's where we would choose our partition. Okay, we could throw this into R, and there is a library called rpart. And so here I can kind of take my data frame. X is 1, 2, 3, 4, 5, and y is 1, 1, 3, 7, and 8. And I can say, hey, make a decision tree. Okay, predict y based on x, data equals df. Now I throw in this thing called control. You can control how rpart makes splits and whatnot. And generally, once it gets to maybe 5 observations in a final bucket, rpart doesn't make any further splits. But here I wanted to try to make a split, so I use rpart control there. And this is the resulting tree. This might be a little bit hard to read, but you can see the split happens at x is 3.5. So the way you read this is you have the root node, which has 5 observations, and then your split happens at x being less than 3.5 versus x being greater than 3.5. Okay, you have 3 observations that are where x is less than 3.5, 2 observations where x is greater than 3.5, which matches exactly with our diagram right here, okay, and our table right here, okay, on 14. And this over here is your predicted value. When x is less than 3.5, the value we predict is 1.667, okay, which is exactly what we have here, okay? And then when x is greater than 3.5, our predicted value is 7.5, okay? And then whereas in the root node with all 5 observations, our predicted value would have been 4. And then here's your total kind of RSS, residual sum of squares. In the root node, it was 44. And then after the split, you have an RSS of each kind of node. And this is kind of, back on this slide, I said your total RSS is 3.1667. But if you just add the 2 for the second node, you'd see you'd get 0.5. And then if you add up these 3, you would get 2.1, 2 point something, 2.667, okay? So if you add those up, you get 2.667 and 0.5. Okay. And so that's, I kind of detailed that out here, but this arrives at the same decision tree that we created when we kind of tested out our splits manually and did all of the same calculations. So, so indeed, when R fits a decision tree, we get the same kind of value there. Okay, you can also kind of call summary on R part, and you get an improvement here. Here it says improvement of 0.9280303. Okay, 0.9280303. So that what that means is, you know, that number comes from before we did any kind of split. The RSS of our 5 data points was 44. If you just predict 4 for everybody, your residual sum of squares is 44 in total. After you do the split, your residual sum of squares is only 3.1667. So it reduced 40.833, or a reduction of 92.8%. So that's where this improvement of 0.928 is calculated. And I guess if you wanted to kind of have an R squared value for a decision tree, this decision tree would have an R squared value of 0.928. Okay, this would correspond also to what's known as a complexity parameter. So decision trees will have these, you'll have this kind of column called complexity parameter, and this kind of is related to kind of how much improvement do you get with each of these kind of splits that can be produced. Okay, you can plot the tree. This is the dumbest plot. Basically, it just says, here's a question: x is x less than 3.5? And if the answer is yes, you go down the left side and you'd predict 1.667. And if the answer is no, you go down the other side and you'd predict 7.5. This is, there are much better, I guess this is the base plot function for a tree. And then if you have like a more complicated tree, it will have kind of further splits. And then you have to also call text, otherwise you'll just have these splits that don't do anything. So it's not a great tool. There's better things for visualizing regression trees. Okay, you can do the same with a bigger data set. So if you don't have a toy data set, you just have to consider more splits, and you consider all of your variables. So let's say you had a data set with 5 variables and 100 observations. Technically, you would have 495 splits to consider, because for your 100 observations, assuming you have 100 unique values, there would be like 99 possible places where you could split that one variable. Okay, and then you have to consider all 99 splits for variable 1. Then you would consider all 99 possible splits for variable 2, and you consider all 5 variables and all possible splits, and basically, when you ask R to create a decision tree, it's going to go through every single one. So if you have a big data set, it can be computationally expensive to calculate a decision tree. I guess there are some kind of methods that could speed things up, but basically that's how a regression tree will get calculated. is that it will consider every possible split. Okay. And then once you form a split, now you just have a kind of a sub-segment of the data. So you might have originally 100 observations in your full data set, and then you create a split, and it splits it into a group of 40 and a group of 60. Okay. You go over to kind of one partition, that group of 40, and then you repeat the same process. You consider all 5 variables, and now you have 39 possible splits for each of the 5 variables. So you'd have 39 times 5, whatever, so around 200, 195 possible splits to consider, and you split that, and maybe that set of 40 gets split into 20 and 20. Then you go to that group of 20, and you consider all possible splits. Okay, and you keep going until you reach some kind of stopping criterion. Usually the stopping criterion is you need once you get down to, say, 6 observations in a bucket, then you say, all right, that's good enough. Okay, or you might say, like, once you go 3 levels deep, then we'll stop there, or something like that. Okay, so you have some kind of artificial stopping criterion, and that will go. Okay, if you don't specify that, then the tree could kind of keep going until each bucket has 1 observation in it. Okay, and that's going to be definitely an overfit thing, right? Because it will be kind of like, it might first, the questions might start, in the beginning, it'll be like maybe general questions, are you a man, yes or no? And then, are you over 30, under 30? And then, once you get down to a certain bucket, it might have to start looking at different variables. And it will be like, is your shoe size between 8 and 10? And then, did you, eat cereal for breakfast this morning? And then now we finally identified one bucket where there's one person, and we can predict this thing accurately, okay? But it's certainly not going to generalize to the greater population. So, that's, but you would get 100% R-squared value, right? Because you're going to predict everybody there. But if you do overfit your thing, you can prune the tree, and we're out of time here. But basically, so here I set bad kind of criterion here, and it split everything, and so there's basically just one value, and we have no deviations. All right, and so we're predicting every single value perfectly here. But we've overfit our data. Okay, and so you can go back, and this is known as pruning the tree. So they're really leaning heavily into this tree metaphor. Okay, so if you have too many branches in a tree, I guess the gardener would then prune the tree or whatever. Have you guys been to the Getty Center and you go to the garden and those trees are like perfectly manicured and pruned? Anyway, I was just thinking about pruning trees, but anyway, that's what you have, and you can go through and basically you specify like what complexity parameter you want. And so this first split had a complexity parameter of 0.928, and then the next split is only able to improve it by like 6%, and then the third split only improves it by 0.01. So that would be like further splitting the data between here and here. So you hardly get anything, and so you can say, hey, I want a minimum complexity parameter, minimum improvement of at least 2%, and that will create that will get rid of one of those splits, and so on and so forth. Okay, but anyway, that's kind of how decision trees work. I did another example with this CARS data set, but there is a little bit of kind of when you do like cross-validation and stuff, there's different things that could happen. So, but there's that for decision trees. Okay, we'll wrap things up here, and I don't know, maybe I'll talk a little bit more about this because you can get into like boosting and things like that for like XGBoost and stuff. Those are all based off of trees. Okay, we'll call it quits here, and we'll see you guys on Friday.